Before we start on 6.2, I wanted to go back through and look at number 28 from 6.1. It'll be important for the lesson we're doing today. So if you haven't already, pause this and run through these derivative rules really quick to make sure you remember them all, and then we'll go through them together. So if you look at this first one, right, derivative of e to the x is e to the x. So that's important because that means that if I integrate e to the x, right, if I'm working backwards, this still comes out to be e to the x. Derivative of ln of x is 1 over x. Hey, that means that the integral of 1 over x dx, right, I'm working backwards. I forgot my plus c there, sorry. Comes out to be the ln of x plus c. So we can just, by knowing the derivative rules, we also know the integral rules. Derivative of sine of x is the cosine of x. Well, that means the integral of the cosine of x, right, if I'm working backwards, is the sine of x. This is where it gets a little bit trickier. We know the derivative of the cosine of x is negative sine of x. What that means is if I want to integrate the sine of x, I've got to work backwards. The sign changes. When I go from when I take the derivative of cosine to the sine, it changes. Sorry, derivative of cosine and get negative sine, the sign changes. So if I work backwards, the sign still has to change. So the integral of the sine of x is negative sine of x. Derivative of tangent of x is secant squared of x. Well, that means the integral of secant squared of x is going to be the tangent of x plus c. I've got my plus c's down there. The derivative of cotangent of x is a negative cosecant squared of x. That means the integral of the cosecant squared of x is a negative cotangent of x. It flips the sign. So if you change the sign when you take the derivative, then if you're going backwards, you still have to change the sign. Derivative of secant of x is the secant tangent of x. So the integral of secant tangent of x is secant. The derivative of cosecant of x is a negative cosecant of x cotangent of x. So again, if you're going backwards, the sign has to change. You have to flip the signs. The derivative of a to the x, remember, it's still a to the x, but you have to times it by the ln of a. So if I'm working backwards, just think of this with me, and I have the integral of a to the x. Right? If I know I have to times by the ln of x when I take the derivative. So if I go backwards, instead of timesing by the ln of x, I have to divide by the ln of x, or not ln of x, sorry, the ln of a. The derivative of log base a of x is 1 over x ln of a. So really I end up dividing by the ln of a. Well, that means if I'm working backwards, I have to times by the ln of a. And we'll get into that one more another day, not today. Wait, but if you think of all those derivative rules, we have to make this connection, because if you know the derivative rules, you also know the integral rules. So if you look in your book there on 6.1, these are the rules we're going to cover today, right? The integral of e to the x is still just e to the x plus c. The integral of a to the x, when we take the derivative, you times by the ln of a, so when you integrate it, you divide by the ln of a. The integral of the cosine is the sine of x plus c. The integral of the sine of x is negative cosine. So think of this, when I take the derivative of cosine, I have to change the sign. It's a negative sign. So when I do that same rule backwards, I still have to change the sign. The integral of secant squared of x is the tangent of x. Integral of cosecant squared of x is the negative cotangent of x. Again, when I take the derivative of cotangent of x, I get a negative cosecant squared. The sign changes. So when I integrate, the sign has to change. The integral of secant of x tangent of x is the secant of x plus c. And the integral of cosecant cotangent of x is a negative cosecant of x plus c. So if you think of it, when I take the derivative on all those rules where the sign changes, when I'm working backwards and I'm integrating, those signs have to change also. That gets a little bit tricky. One little thing the book has here that can help you remember this says, if you read down here, it says, in most common errors are made with signs. You can hopefully see that from up above. This little diagram can help you. So, you know, in the corner of your assignment, in the corner of your test, if you want to make this diagram, and we have, it's kind of like a unit circle. The cosine is positive over here, right? It's a positive 1. It's a negative 1 over there, so positive, negative. The sign is a positive 1 here and a negative 1 there, so positive, negative. So if you draw this little diagram, and then the antiderivatives go this way. So if I go from cosine to sine, it's positive. If I go from sine to cosine, it changes to negative. The derivatives go clockwise. So if I start up here, I go sine to cosine, it's positive. If I go from cosine to sine, it's a negative. So if that's helpful to you, you can. Personally, I think it's easier just to think about the original derivative rules. If the sign changes when I take the derivative, then when I work backwards, the sign also has to change. Anyway, whatever works for you, but just have, again, that's probably one of the biggest pitfalls with these is missing a sign or getting a sign wrong. Okay, so let's go do some practice with this. So a couple things that'll help you with on these problems. Make sure when you go do these integrals, if there is a scalar factor like -3, move it out in front so it's just out of the way. So I have -3 out in front, integral of, now I just have the sine of x dx. So now I can just integrate this. This is one of our rules, right? So what do I take the derivative to get the sine? It's the cosine. And don't forget your plus c. Okay, next one. Another rule from yesterday. Remember, if you have separate terms separated by a plus or a minus, you can separate those. I'm going to do that on this problem. I'm going to write it as being the integral of e to the x dx minus the integral of 2 to the x dx. Okay, now let's integrate it separately. E to the x is easy. All right, what do I take the derivative to get e to the x? It's e to the x. So the integral of e to the x is e to the x. Okay, integrating 2 to the x power. So remember, normally it stays the same, 2 to the x times by the ln of 2. But because I'm working backwards, it's still going to be 2 to the x, but I'm going to divide by the ln of 2. And don't forget the plus c. Okay, and that should be our answer right there. If you look at this third example, so again, I have separate terms here, so I'm going to go through and separate these terms. So I'm going to write it as being the integral of, I'm going to move the 5 out there, 5t to the 2/3, right? The cube root of t squared is t to the 2/3, plus I'm going to move the 3 out, 3 integral of the cosine of t, dt, minus 1 dt. Now I can just do each of these separate. So we're going to start with that first one. So it's going to be 5 times t to the 2/3. I'm going to add 1 to the power, so that'd be t to the 5/3. Then I have to divide by 5/3, and to divide by 5/3 is the same as timesing by 3/5. So you got 3/5 times 5 times t to the 5/3. Okay, plus 3. Integrate the cosine. So integrate the cosine, that's just the sine of t. Minus, and integrate 1. And don't forget my plus c. We can do a little simplifying. Right? I've got 3/5 times 5. Those 5s just cancel out. 3t to the 5/3 plus 3 sine of t minus t plus c. Okay, and there's my answer. So again, just doing it piece by piece and then applying your rules. This is the power rule. This is my rule for integrating the cosine. That's my rule for integrating a constant. Hey, this next one's a little bit tricky. At least it looks different because it's got that 4 down below. If it's just a constant on the bottom, you can always do this. I can think of that as being, this is the same thing, 1/4 times secant of y tangent of y. Right, those are the same thing. Secant of y tangent of y over 4 is the same as 1/4 times that. And the reason that's helpful is because 1/4 now is just a scalar multiple. So I can just move it out in front. Okay, so I just have to integrate this. Well, what do I take the derivative of? What do I take the derivative of that gives me secant of y tangent of y? And that's the secant. So when I integrate that, this is to become 1/4 times by the secant of y. And don't forget the plus c on the end there. Okay, Last one, last example here. This one gives us an initial condition. So it tells me f prime of x equals a cosecant of x squared. But it gives me this initial condition, and wants me to find f of x. What that means is we can figure out what c is equal to on this problem. Hey, before I start here, just a side note, make sure we remember or recognize that this is exactly the same thing as the cosecant of x squared. This is a form we're used to seeing it in, right? So now let's integrate that. So f of x is going to be equal to, and all you got to think is, what do I take the derivative of to get the cosecant squared of x? And that's the cotangent of x. Now, those switch signs. I take the derivative of the cotangent of x. It's a negative cosecant squared of x. So when I go backwards, I still have to change the sign. It's going to be a negative cotangent of x plus c. Now, normally we'd be done there, right? But because I have this initial condition, I can figure out what c is. So I know when I plug in 5/4, it has to come out to be 3. So y has to be equal 3 when I plug in 5/4. So I'm going to plug in 5/4, it has to equal 3. I'll solve for c. So I need my units. I need to draw my reference triangle. 5 pi over 4 is 1 and 1/4 pi. It's right there. So this is 1/4 pi, which is 45 degrees. 45 degrees is 1 square root of 2. Make sure you got the signs right. I'm going to the left, so the x is -1. I'm going down, so y is -1. Cotangent, tangent is opposite over adjacent. So cotangent is adjacent over opposite. Either way, it's -1 over -1. So you get 3 equals a negative, and this part right here comes out to be 1, right? -1 over -1. Add the 1 over. So c is equal to 4. So my actual function, right? This was my function, except for I didn't know what c was. So my answer is f of x is going to equal a negative cotangent of x. Sorry, I hit a dead spot there. Negative cotangent of x plus 4. And we got it there. So just like before, if you have an initial condition, make sure you go back and solve for c. These could be tricky. Like before, sometimes we have to manipulate it algebraically, or we have to use some of our trig identities to change the form. Our goal always, though, like what we're focused on, if you come back to here, is if you're working on a trig problem, if I can make it look like either a sine, secant squared, cosine, cosecant squared, cosecant cotangent, or secant tangent. If I can make it look like one of those, then I can always integrate it. Sometimes they won't. Let me just show you a couple things from your assignment. You know, on that first one, we can just separate those two. Integral of secant squared minus the integral of 2. When you have theta, don't let that bother you. This one, you're still going to do the power rule, right? When I integrate, I'll go theta, add 1 to the power, and divide it by it's just like an x squared. So don't let that bother you. But the ones I really want to look at is number 4. Number 4 is a little tricky. You do not have a rule for 1 over the sine squared. So I want to try rewriting that in a form that I do have a rule for. Well, remember that the sine is the reciprocal of the cosecant. So 1 over the sine squared is really the same thing as the integral of the cosecant squared of y dy. Those are the same. That is the same thing as that. Now we have a rule for the cosecant squared. So now you can look at your list of integral rules and find that. On this one, right, you can move that e to the x up to the top. So you'd have the integral of 2e to the x plus x to the 1/2. Now you can separate those and integrate those from there. Number 6, again, you can break that fraction apart. There's one more I wanted to show you. Number 9. Again, break that apart. You can go the integral of 3 over the cosine squared of x plus right now we got the integral of, I can pull the 3 out. I'm going to separate those. Cosine squared of x dx plus, and that would just be 1 of 1 dx. That's easy now because that's just a constant. But again, we get down to this one, I don't have anything for 1 over the cosine squared, but remember, it's the reciprocal of the secant. So always, if you can, try to manipulate it, rewrite it, use our trig identities to rewrite those in a form that we can actually integrate. I think that's most of it. This one, I get 1 over the sine times 1 over the tangent. Well, 1 over the sine is the cosecant, and 1 over the tangent is the cotangent. So again, if you rewrite them, now this, I should put them together, I guess. Those two together, we have an integral rule for that. So there's some tricky stuff here. Make sure you use all the properties we know, and try to rewrite them, try to make them look like that. And there'll be some questions. There'll be some you get stuck on. Let me know if you do, and I can help you with questions that you have. All right, thank you.